Hello, my name is Juha Tuomola, and today I am going to give you a short introduction to Tanktwo string battery simulation tool. String batteries are based on completely new battery technology that is targeted especially for electrical vehicles. String batteries offer a lot of benefits compared to traditional batteries, like much lower cost, extremely fast charging, and short design cycle for new batteries. From the engineering point of view, a string battery is like a container that encloses different numbers of electrochemical cells called string cells. They are like small single batteries that are placed inside a battery container in random order and orientation. Like a typical battery cell, a string cell has electrical terminals on it. As normal cell has just two terminals, positive and negative, a string cell typically has 6, but the number can be anything from 2 to, let's say, 30. These terminals are special in a way that any of them can be used as positive or negative, and any of them can be disconnected or bypassed with any other terminal in the cell. In this tool, the terminals are actually called as channels. Alright, about the tool. This version is still early development version, but it's still able to show some key points of string batteries. The tool is developed mainly for design engineers and for those that are generally interested in this new technology and want to understand its capabilities. On the opening view of the tool, you can specify the main parameters of the string battery. You can define the capacity, volume, weight, size, or number of the cells. Down here you can specify the string cell properties as well. The shape of the cell is an ellipsoid, which parameters you can freely modify. The default shape is based on existing string cell design, and it's proven to be quite good. Alright, let's start with default values. Pressing the Create Battery button creates the wanted number of cells as rigid bodies and drops them to a defined container space. Okay, now the cells are randomly placed in the battery and squeezed tightly together so that they cannot move. This is important because we want to make and maintain proper electrical connections between the cells. Just to demonstrate the effect of the shape, let's try the same battery with ball-shaped cells. Here you can see how the balls do not fill the space as nicely as the ellipsoids did. There are a lot of voids, and if you could shake the container, you would notice that several balls can move, which is obviously not a good thing if you are trying to form electrical connections. Let's change the number of cells to 100 and the shape back to the default. The random packing with different shapes have been studied, and the ellipsoids used here by default have been found to be excellent of forming a large number of contacts. This prevents them from moving in relation to each other. At the same time, this shape fills the space better than basically any geometry. This maximizes the capacity to volume ratio of the battery. From here you can try different display modes like transparency, turn grid on or off, and change the background color of the model window and shots. More interestingly, you can study how many contacts the simulated cells actually are making with each other. With this slider here you can inspect the number of contacts. As you can see, the minimum number of contacts here is 5. And the maximum is 10. On the Contact tab, you can analyze how the contact points between the cells are spread for the surface area of the cells. Basically, you can visually detect, for example, areas where the terminals should be placed. You can also create a heat map that shows visually if some areas are more likely to have contacts than others. Here on the Channel tab you can specify the terminals that exist on the inside surfaces of the battery. These terminals connect the electrical circuits from the cells to the battery. On the next tab you can specify the terminals for the cells. Let's select the one with 6 terminals. The tool lets you select from 12 different terminal combinations that have from 2 to 26 terminals. You can also freely change the positions and sizes of each terminal combination. Okay, now the terminals have been created for both battery and cells. The green color in terminal here shows that there is actually an electrical connection between the battery terminal and at least one cell terminal. On the display tab you can now also inspect the number of electrical connections between the cells. This is a pretty important parameter because each cell needs at least 2 connected terminals to be functional. Here, 3 cells have only 1 terminal connected, which means that they cannot be used. Several cells have all 6 terminals connected. We have also other interesting representations to be checked here. Let's first see the network of the electrical circuit that has been formed between the cells and the battery. The yellow nodes are the functional cells, red nodes are the non-functional. Green links and blue nodes are electrical connections from terminal to terminal. On detailed network representation you can see even more details about the connection network. Here each connected terminal is represented as blue node next to the cell. This network is used as a starting point for all routing algorithms. After the cells are placed in the battery container, the first problem is the network mapping, so that the location of each individual cell in the network is known. This is done by a process where certain wall terminals are connected to current source and rest of them are grounded. To simulate this we need to be able to solve electrical circuit simulations, just like for example SPICE circuit simulator does. Current map here shows presentation of currents through the cell network, while cells are in high impedance mode. At this point let's also open the command prompt and info screen to query some of the currents and voltages. By clicking the nodes or links here, the info screen shows their voltage, current and resistance values. After the mapping is completed, the battery uses network algorithms to generate as many as possible disjoint connections from one battery terminal to other. This is done currently with proper shortest path algorithms. These paths can be seen here. From this view it is probably the easiest to understand the concept of the string battery. Think one battery wall as a negative and another wall as a positive battery terminal. Now we have just a bunch of series connected cell strings, which can be combined with the aid of voltage converters. The problem remaining here is that the maximum output power would be rather limited here, because only maybe half of the cells are utilized. To improve the situation, we can use these initial strings as seeds to create longer ones. One by one the strings are released to residual circuit network, and using another network algorithms, new longer strings are created. New algorithms are still under development, but even now we are getting constantly around 90% cell usage for maximum power delivery. This time we got 85 cells, which means 85% cell usage in these strings. The rerouting of the strings can be done during the usage of the battery, which means that also the remaining cells can be utilized. In typical case, there are only 0 to 1% of unusable cells. The last tab is for the design studies to optimize the battery parameters. You can set here measurements and select design parameters and give them range to iterate over. Let's try something simple. Measurement here is the average contact count per cell. Design parameters are the aspect ratios of the cell, which defines the shape of the ellipsoid. Let's define them so that we start from ball shape and end up with the default ellipsoid shape. Okay, we got 4 trials. This will take some time because the simulator needs to run 4 complete cycles from the beginning. On an exhaustive analysis, you can have thousands of trials and the study can last overnight. Alright, now the study is ready. As you can see here, the ellipsoid has by average 2 more contacts comparing to ball. Let's run one more study. Let's see how different numbers of terminals will affect to the distribution of connected terminals per cell. The type 2 is the simplest possible terminal type with 2 terminals. Type 7 has 6 terminals and type 12 has already 18 terminals. Here you can see that increasing complexity helps first but evens out quickly. Even the cell with 2 terminals could be made to work, but as the histogram shows, there are already 20% of cells with less than 2 connected terminals. These cells would be non-functional to start with. Cell with 6 terminals seems to be clear winner here, being only slightly worse than the cell with 18 terminals. Alright, this was a short introduction to string battery simulation tool and the new string battery technology. Thanks for watching and remember to visit tanktwo.com for further information.